So we are going to do exactly the same for the common gate stage amplifier, and then we start with the nuller approximation for this stage. So let's see. So we have the nuller. It will look something like this. Then we have the source resistance here, and then in parallel to a current source. So we have the source here, plus, minus, minus, plus, and then we have the load here. So when we use the nuller, we have that all this current it is going to flow like this and go out like this. Okay, and we can see here that this configuration works as a current buffer. And our nuller approximation tells us that the current gain it is going to be equal to 1. Okay, so we will have current equal to 1, and then now let's replace the nuller by a transistor small signal model, and we're going to do exactly the same as we did with the common drain. Now we are going to let the transconductance to become infinite. Okay, when we let the transconductance to become infinite, same thing, the input of the voltage controlled current source, the input, okay, this input here, the input here becomes 0 volt. We set this transconductance to infinite due to the feedback. It means that the voltage here will be 0 volt, and then we can see the following properties. We have that one terminal of the capacitor CGD, it is connected here to this node. I'm going to put it ground as a reference here. It is going to be grounded here, and the other terminal is connected to the output. Assuming that we have a infinite transconductance, okay, then the output of my amplifier here works pretty much like approaches the nuller that has a extremely high output impedance. So this is basically a current buffer. So I expect to have extremely large output impedance here, so that all the current goes directly to the load. So here, if this transconductance is infinite, basically it creates extremely large output impedance that allows the current to flow toward the load, all the current to go towards the load. Yeah, under that condition, we see that this capacitance here, this capacitance CGD here, that has one terminal grounded, appears in parallel to zeta L. Okay, so we can see this in the following way, so that we have this capacitance that it is grounded one terminal connected to the output here, that will be CGD here connected, and then even if we have an infinite transconductance here, the gain will be limited at higher frequencies because this capacitor CGD starts to shunt signal to ground, so there will be there will be a pole in the asymptotic gain. So again, assuming that the theta L is resistive, then we will have a pole that it is located at 1 plus S CGD times RL. So this is a single pole system. This pole in the asymptotic gain will become 0 in the loop gain, and it is a phantom 0. Okay, so we have all the information that we need from the null approximation and the asymptotic model. Now we go forward and calculate the loop gain, and we do exactly the same as we did before. So now we are going to replace our transconductance amplifier with a test current, and then we are going to remove our source, our current source here, and then we are going to calculate how much VGS comes back, because that will be my feedback factor beta. So we do this calculation here. After we remove the source and we place the test current, we have the following circuit. And then we can calculate beta here. We have this current, it is going down. We can calculate all the current that comes in this direction here, and that will be current divider. So we have at IT times that will be RDS divided by RDS plus theta S plus theta L. That will be the current that it is flowing in this branch. But now I need to get the voltage. I am actually interested in this voltage, so this current is going to produce a voltage drop here that is equal to this current multiplied by this impedance. And see, the current flows in this direction going up. It is going to produce a voltage drop that is opposite to VGS, so there will be like this. VGS is going to be equal to minus IT times RDS theta S divided by RDS plus theta S plus theta L. Okay, so I calculate beta, VGS divided by IT, and then we get that will be RDS theta S, and that will be RDS plus theta S plus theta L. And then I multiply this by my amplifying parameter, that is the transconductance, and then I get the total loop gain. Okay, so that will be my loop gain, and then I can do the following observations here, precisely as we saw before. We have a phantom 0 that it is located, if the load is resistive, it will be located at RSCGD. Okay, we found this one by analyzing the poles in the asymptotic gain. So we have that, we know the position of the 0 in the loop gain. Then we know that the D parameter will be close to 1 because it's working as a current buffer. We saw it from the asymptotic gain. Then when we write the whole gain, we will have that will be equal to minus I infinite times AB beta divided 1 minus a beta, and then that will be minus 1 times, and then we have our equation here that we are going actually to simplify it a little bit. If RDS are extremely large, which is typically the case, we have that AB0 will be equal to minus GM times zeta s. Okay, if RDS is very large, then I can basically omit these ones, and then that will get simplified. So under this condition, that then we might get that this is approximately GM zeta s divided by 1 minus GM zeta s, and then at the end of the day we will have GM zeta s divided by 1 plus GM zeta s, which is exactly the same as we got for the common drain amplifier, and that was if we have RDS, it is extremely large. If it is not, we will have to take the whole equation. Okay, so we have the following things. Only the D parameter, that it is the current gain, has changed, and it is approximately 1. It is always going to be smaller than 1, so this takes value close to 1. The other parameters, interestingly, they are exactly the same as in the common source stage. The others are not affected. Now, when we analyze the equation, we can see something also that is interesting. Let's take it the first one, this one. If the source resistance is small or close to 0, then basically we have that the feedback disappears. The feedback disappears, and then the current gain is equal to 0. So what happens when the voltage, when the source resistance is 0? When the voltage source is, when the source resistance is 0, this is a wrong model. If the source resistance is 0, it should have been a voltage source. Small resistance are associated with voltage sources, not with current sources. So that will be a wrong selection of an amplifier. So it shouldn't be that the source resistance in a current source is close to 0. So that will kill immediately the feedback, and that stage will not work. Another observation, it is that the load is also very important, and that is not so evident, and sometimes we forget. We can see here, it is actually the load impedance, the one it is bringing the feedback current through zeta s. Okay, if this impedance it is extremely large, then the voltage that is coming back to CGS is very small, will be very small, and if it is infinite, then it will be totally disconnected. So that is an important observation. In a common gate amplifier, it is not expecting to have very large output resistances here. It will just break the loop. Okay, so we have studied the common source stage, the common drain stage or voltage buffer, and the common gate stage current buffer. There are other single stage amplifiers that are also interesting for us, and these are the following stages. We can have a common source stage in which I add a resistor to the source, so I don't connect it directly to the common node ground, so I connected it through a resistance here. So this is called the series stage. Another that it is very interesting, it is the shunt stage. Shunt stage, I connect the drain to the gate connect an impedance. So we are going to analyze these stages. And we will start with the series stage. So we take the series stage here, and we replace the small signal model. We replace the transconductance with a test current. This will be the circuit that we need to analyze in order to extract the beta factor. So remember that we have here CGD, we have here CGS, and we have here RDS. And when we replace all the small signal model, we will have the following circuit that it is here that we will have to analyze. Okay, so the best way to analyze this circuit is to use an example, and then we are going to take our first example in cadence. Okay, so let's going to assume that we have a transistor that has been biased. It has been biased with 10 microamps. Okay, it is 10 microamps. We have biased this at 0.9 volts. It has some dimensions here. And we extract the small signal parameters for this transistor using the templates that we have already created in lab 1. And we connect it like this. We have RF here connecting the source to the ground through these 100 kilo resistors. The voltage source has an impedance of 1 kilo ohm, and we are loading the output with 1 mega ohm to ground. So let's take a look. How can we calculate the voltage gain of this amplifier under these conditions? So first we are going to do a hand calculation using the asymptotic model, and then for that we just draw the circuit assuming that we have a nuller here, and then we will have this resistance RF, and then we will have this resistance RL, the load resistance here, and then I will have my source here, in, that will be RS, and then this will be V out here. So I calculate V out assuming that I have an ideal amplifier and nuller, and then I can do immediate calculations here. There is no current flowing here, that will be V in, and then it becomes just a transconductance amplifier here. The current that flows here will be V in divided by RF, and all this current it is going to flow here because there is no current flowing here at the input of the nuller. So all this current is going to be diverted towards the load. It's going to pass like this also, and it is going to produce a voltage drop here that it is equal to minus V out. It is going to be equal to minus V in divided by RF multiplied by RL. Also the voltage gain is going to be equal to minus RL divided by RF. And then we have 1 mega ohm here, 100 kilo here, the voltage gain, assuming a nuller implementation, that is going to be equal to 10, minus 10. Okay, so we have this. Now let's calculate the beta factor. The beta factor, for that we will we will need to use this model, and when we use this model, we see that there will be some current that goes in this direction, and this is the current that it is going to produce BGS here. Okay, so this is actually the arrow, it is in the other direction, so it is going to be like this, and the voltage is going to be like this. So what is this current? So we can calculate it like this. That will be IT, my test current, multiplied by RDS. This is a current divider, divided by RDS plus, and that will be the series of these two resistances there. So this is an open circuit, this is a capacitor is open, so there is no current flowing through zeta S, at least at low frequency. So that will be zeta F plus zeta L. I will have that current flowing there, and then the voltage, it is just multiplied by zeta F, and that will make it VGS equal, and then there will be a minus because the signs are plus minus opposite to VGS. Also, the beta factor VGS divided by IT will be equal to RDS zeta F divided by RDS plus zeta F plus zeta L, and yeah, then that will be all the calculations. So we have is RDS, RF, RDS plus RL, RF. Okay, I am assuming that these are resistive, so if zeta F is equal to RS and zeta L is equal to our resistor RL, assuming resistive loads, which are here, so we can see that they are resistive. So we have the following beta. So if I replace the small signal values and that I have it here, I will get the following component at DC, minus 21.7. Okay, I can do simplifications here. For instance, if RDS is very large, then the loop gain will be minus 22.7, but I have to check. Sometimes I make very little error, introduce very little error doing simplifications, but they might be worth. Then the loop gain, we have calculated the loop gain, then we have calculated also the asymptotic gain, then I can calculate the closed loop gain. The closed loop gain will be at low frequencies 9.55. Okay, and this is with very simple hand calculations. Now we are going to calculate the poles of the loop gain. Okay, and then for that we are going to use a tool from the basic electrical principles course. We are going to use the open circuit time constants method. And what does this method tells me? I can calculate the position that is the position of a pole that is associated to a capacitance by estimating all the resistance that this capacitance is facing. So if I have a capacitor in a circuit, this capacitance will be associated to a pole. Okay, equivalent resistance, we have the capacitance, and then this will introduce a pole equal to 1 over C resistance equivalent. So I will take the bigger capacitances, and then find the equivalent resistance that it is facing this capacitor, and then I can calculate the poles. Now we have to be very careful when we use the open circuit time constant. It is extremely simple method, but we can make a lot of mistakes because it is only valid if there are no zeros presented in the transfer function. So we should expect to make some mistakes. We're going to check with the simulator if the mistakes are extremely large, then we have to correct for them. And we have already some hints regarding what happened when we have zeros. CGD, for instance, introduce zeros in the transfer function, introduce Miller effect, and introduce pole splitting. So whenever we had a wrong estimation with the poles, we will have to take into consideration CGD, Miller capacitance, pole splitting. Normally the method gives us a really good approximation of the poles for most cases. So let's take a look. Let's take a look the position of the poles. Let's see. We're going to merge some capacitors. So the simulator gives us separated the CGS and CGB. So we are just going to merge them in a big CGS, all the capacitance that is connected between gate source and gate to bulk. And we are going to do the same for CDS. CDS and CDB, we are going to merge in a big capacitance just to make it a little bit simple, the calculation. Normally we don't introduce large errors by doing this. Okay, so let's take a look to the position of the capacitors. And then we can draw very quickly the circuit again. So we have CGD, we have CGS, we have our test current here, and we have RDS. We have the total capacitance here at the drain source, here also drain source. We have our feedback resistor here, RF, and then we have a load resistor here, RL, and then we have our resistor RS. So that was our let's say our model to calculate the beta, okay, by replacing the transconductance with the test current source. Now let's take first CGS. We are going to assume at the beginning that we don't have CGD, just for simplicity. If our result is not accurate, then we are going to take it into consideration. And normally CGD is not a big capacitor, but it can play an important role if there is Miller or pole splitting. So let's assume for a second that there is not, and then we will add it later if we find that we are way off our calculations. So our model for CGS, for the input pole, we will have CGS. We will have resistor RS here. We will have resistor RF. I remove the current source, and and then I will have RDS here, and then I will have RL. So I remove the other sources. In this case there is only one source, and I remove the other capacitor, so I only leave capacitor CGS right now here. So we have the following model, and I need to find what is the resistance that this capacitor CGS it is facing, and then the first thing that I can notice is that these two resistors are in series. They are in series, and then so I have to add them first, and then these ones are in parallel. Here, and at the end RS is going to be in series with all that. So the equivalent resistance, we call it equivalent for CGS, that will be equal to, and then we have RS appears directly here. It will be RS plus, and then we have RF that is in parallel to RDS plus RL. Okay, so that will be my equivalent resistance. And the position of the pole, we call it pole 1, will be equal to 1 divided by R equivalent CGS times CGS. Okay, so and that will be the position of the pole number 1, and then we can take this one in frequency. That will be P1 divided by 2P. When I replace the values, and I have a script that MATLAB that is actually doing that. It is very convenient to have this scripted. I have the values of the small signal parameter extracted from cadence here, from our templates, and then I have these values for the. I can calculate directly the equivalent resistance, and I calculate the input pole here. So for this particular pole 1, I got 5.79 megahertz, 5.79 megahertz. So this is around 5.79 megahertz. Okay, the position of the first pole. Then we do the same, and we should check, and we're going to check a little bit later with the tool if we need to do some correction due to CGD. For the position of the other pole, then I also need to draw the model. So we're going to take, on the other hand, that will be CDS, the output pole that is located here. So we will have capacitor CDS, there will be resistance RL. This capacitor is in parallel to RDS. RF, it is coming down, and then RF, it is connected to also to RL, and then we have RS here that it is disconnected because yeah, there is no capacitor to CGD or CGS. So for low frequency, this capacitor is completely disconnected. So let's find the resistance that it is facing CDS. So that will be R equivalent for CDS is going to be equal to, and then we can see directly that these two resistors are in series and those will be in parallel to RDS. So we can do RDS in parallel to RF plus RL. Okay, and then we can calculate the position of the second pole. This will be around RQCDS times CDS, and that will be FP1, FP2 divided by 2P, and then for this one that will be around 1.2 megahertz, around 1.2 megahertz. Okay, so now let's take a look what the simulator says.